session, we have derived the expression for the stagnation temperature as a ratio T naught by T is equal to 1 plus gamma is 1 by 2 mTm squared. Here the T naught stands for the stagnation temperature and T stands for the static temperature and M stands for the Mach number and the gamma is nothing but your specific capacity ratio. There is nothing but Cp by Cv. This stagnation state is obtained by adiabatically decelerating the flow to zero velocity at zero elevation. So these are the things which we have discussed in the last session. Today, let us explore more about isentropic relations and how from these isentropic relations we will be able to establish stagnation pressure and stagnation states. So today, from the help of isentropic relations, we are going to arrive at stagnation pressures or stagnation pressure and stagnation states. So this one we are going to arrive at. So what is meant by isentropic process? First of all, if you want to attain isentropic relation, we should know what is the isentropic process. The isentropic process is also known as reversible adiabatic process. Is also known as what? Reversible adiabatic process. The relationship which is obtained by considering a process to be reversible adiabatic is called as isentropic relation. For example, let us consider a process taking from point 1 and reaches the point 2. These are the end states 1 to 2. And let the pressure be P along the y-axis and specific volume along the x-axis. Now this process, it is going to be reversible. What is reversible? If I can go from 1 to 2 and once again if I can march backwards from 2 to 1 and if I can reach once again back to point 1, the process called as reversible process. But in this current globe, there is no process called as reversible. There is no process called as reversible. All the processes are irreversible. What does it mean? I can move from 1 to 2, but it is not possible for me to come once again from 2 to 1 traveling the same path. That is called as what? Irreversible. Then you may have a question. Then why we have to study about this reversible process? So whenever you are doing a process, we will try to achieve as much as close to the reversible. Then our loss will be less. So based on that only, we are going for the reversible process. And one such process called reversible adiabatic process. In case of adiabatic process, there is no heat transfer. Let me take a system like this. I will take a cylinder and a piston arrangement. Let it be a closed system. What will be a closed system? There is no transfer of mass either in or out. So M out is not permitted. At the same time, M dot 1 is also not permitted. But energy transfer can take place. Which means what? Energy can go in and energy can go out. This is nothing but a normal closed system. But if the system undergoes an adiabatic process, which means there is no heat transfer, there is no heat is entering into the system and no heat is leaving the system. This is not allowed. So the heat can come from the surrounding to the system or heat can be going from the system to the surrounding. Both are not permitted. Q in and Q out are not permitted. Then I will ask my students, what happened to the temperature of the system? Let us have some working fluid. What happened to the temperature of the medium? Some other students like me will tell the temperature of the system will remain constant. There will be no change in the temperature. Why? I will ask why. Then the students will tell there is no heat transfer. Since there is no heat transfer, the temperature of the system remains same. Then I will put a question to them. Whether then we call an adiabatic process as isothermal process. Then I ask my students whether we can call the adiabatic process as isothermal process. What is my isentropic process? Temperature remains constant, which means what? T1 equal to T2. Then they will little think, and some of them will tell, no, it can't be. Some of them still tell it's okay. But the reason is, in an adiabatic process, the temperature need not to be constant. Why means, because I can add the energy to the system by moving the piston in. When I am going to compress this piston, what happens means the temperature of the gas will shoot up. So the temperature not only depends upon the energy transfer by heat, it also can shoot up by doing some compression work. So when going to move the piston inwards, the temperature of the system can go high without even giving heat transfer. So please students, have it in your mind that for an adiabatic process, the temperature need not to be constant. Sometimes it can be constant, but it's not always a necessary condition. It may be one of the condition, but not always need to be the satisfying condition. So what I finally want to confirm is that in an adiabatic process, the temperature need not to be constant. So T1 need not to be what? T2. Sometimes it can be equal to T2. But always it need not to be what? T1 equal to T2. So now we have discussed more about adiabatic process. We discussed more about isentropic process, how they are getting differentiated, and what is meant by reversible adiabatic process. So now we discuss about adiabatic process. Now let me take an example. I have a small stone. I am going to throw this stone into a pond, into a lake. What will happen? There is no heat transfer because both the stone and the lake are in the same temperature, and there is no heat transfer happening between the stone and the lake. But definitely this process has irreversibility. This process has what? Irreversibility. Because of the friction, because of the formation of the waves, all these things, there is irreversibility, and hence it is not called as an isentropic process. The throwing of a stone into a lake may be adiabatic process, but need not to be isentropic process because the process is not reversible. The process is irreversible. I hope you got it. So, but for an isentropic process, not only should be adiabatic, but also should be reversible. So, what are the two conditions should be satisfied isentropic? One is adiabatic. The second thing is what? Reversible. So, you have to study this system as separate term. This term as what? Separate term. So, both we have to satisfy. It should be both adiabatic as well as what? Reversible. Okay. Now let us consider this process. This process let us consider reversible adiabatic. Okay. So this process can be given by the general form PV per gamma equal to constant. What does this equation indicate? This equation indicates the general form of an adiabatic process, which means at this point it will be P1 V1 or gamma. At this point it will be what? P2 V2 or gamma. Both these values will be equal to a same constant. I can take some other point here. Let us say this point is 3. So it will be P3 V3 per gamma will be equal to what? P2 V2 per gamma, which will also be equal to what? P1 V1 per gamma. Which means this curve is characterized by this mathematical equation. This curve is characterized by this mathematical equation P per gamma equal to constant. Which means I can apply this equation to both the endpoints 1 and 2. Which means PV per gamma is equal to P1 V1 per gamma, which is equal to what? P2 V2 per gamma. What is the difference between small v and capital V? Even I can write like this. PV per gamma equal to what? P1 V1 per gamma equal to what? P2 V2 per gamma. What is the difference between equation number 1 and 2? In equation 1, I have small v. In equation 2, I have capital V. So what is the difference? This V stands for volume. This V stands for specific volume. So the unit of volume is meter cube. The unit of small v is meter cube per kilogram. So we can use either capital V or small v as per the need. So we can see this is the general format of the reversible adiabatic process. Okay. Now we also know the ideal gas equation. What is the ideal gas equation? PV equal to what? M R T. Where P is the pressure, V is the volume of the process, R is the characteristic gas constant. It is called as characteristics gas constant, and T is the temperature. And T is the temperature. Now P V by M equal to R RT from this equation. What is V by M? V by M is small v. That's what I told. It is meter cube per kilogram. So volume is meter cube, mass is kilogram. So small v is equal to what? Meter cube per kilogram. So this is equal to what? Small v, specific volume. So P into V equal to what? RT. P into V equal to what? RT. Now from this what I want to tell you? P1 V1 equal to RT1. P2 V2 equal to what? RT2. Now my question will be, why not R1 and R2? Can you tell why it is not R1 and R2? Yes, this is because both are the same working fluid. So there is no R1 and R2. The characteristic gas constant remains same. If I am going to consider oxygen as my working fluid, its value is a constant. If I am going to take air, its value is going to be constant. So there is no meaning of having R1 and R2. Both are same. So that only I kept as R only. Now from this, let us keep it is 3, it is 4. From 3, we can get V1 equal to RT1 by P1. Similarly, V2 equal to what? RT2 by P2. Now we call this as equation number 5. This is what? 6. Now substitute the value of V1 and V2 in this equation, equation number 2. Sorry, the equation number 1, because we have made use of the small letters. We have made use of the small letters. So I will try to substitute 5 and 6 in 1 and 2 respectively. So it will be P1 or T1 by P1 whole power gamma equal to what? P2 or T2 by P2 whole power gamma. So I hope what we did now, we got the value of V1, we got the value of P2, substitute over these two equations for V1 and V2. The power gamma is still there, it is there, it is available. So I hope I can erase this one. So now we can see it is P1. What is the power of P1? It is 1. It is 1. R power gamma. Why? This gamma is common to all three terms. So R power gamma. T1 power gamma. P1 power gamma. What I did? I given this power to all the three terms. Similarly on the right hand side. So it will become what? P2 R power gamma. T2 power gamma by P2 power gamma. What is the power of this P2? If there is nothing there, the answer is 1. It is 1. Now this P1 is having the power of gamma. When it is going to take it to the numerator, it will become minus gamma. So it is P1 1 and P1 power minus gamma, which is nothing but P1 minus gamma. P1 1 minus gamma. Can you get the logic? This is having a power of plus gamma, but when I am going to take the numerator, it will become P1 power minus gamma. So we will have P1 and P1 minus gamma. So both have the same base, P1, so it will become what? 1 minus gamma. I hope you can understand. Then R power gamma, T1 power gamma. So there is no need of this division symbol. Here, similarly, you can write on the left hand side. P2, 1 minus gamma, R power gamma, T2 power gamma. In this equation, which term can be striked off? R power gamma and R power gamma can be, because they are having on the both sides, I can divide R power gamma and R power gamma on the both sides. So finally what I got? P1 1 minus gamma into T power gamma equal to P2 1 minus gamma into T2 power gamma. From this, what is P2 1 minus gamma by P1 1 minus gamma? This is T1 power gamma, T2 power gamma. What I did from this expression? I had taken the pressure terms separately, I had taken the temperature terms separately. So from this what I can get it means P2 by P1 whole power 1 minus gamma equal to T1 by T2 whole power gamma. What I did, I had taken 1 minus gamma as common term for both the numerator and denominator, so it made like this. Similarly for T1 and T2, I have taken gamma as the common term. Yeah, we are about to complete now. So here you can see P2 by P1 whole power. I want to take this also as the reciprocal, which means I want the vector side as what? T2 by T1. This is possible only if I want to take the sign of this one. So it has become what? Gamma minus 1. Okay. What I did from here to here? I'll repeat once again. Here T1 by T2 is there. Sorry, T1 by T2 is there. But I want T2 by T1. If I go to T2 by T1, it should become minus gamma. It should become what? Minus gamma. Instead of that, otherwise I will repeat once again. I will make you very easy. I will put like this. P2 by P1 is equal to T1 by T2 whole power gamma by 1 minus gamma. From this step is very easy. Dividing both the powers by what? 1 minus gamma. 1 minus gamma by 1 minus gamma will become 1. This gamma by 1 minus gamma. Now what I am going to do is that P2 by P1 will be equal to what? T2 by T1 whole power gamma by gamma minus 1. What step now we can explain very easily. So I want to replace T1 by T2 as what? T2 by T1, which is nothing but reciprocal, which means I can change the sign of the power. So I have changed the sign as what? Instead of 1 minus gamma, I change it as what? Gamma minus 1. So this is the final expression. This expression is called as isentropic relation. This relation is called as what? Isentropic relation. So P2 by P1 equal to what? T2 by T1 whole power gamma by gamma minus 1. Now we are able to express the pressure in terms of temperature. Now we are able to express the pressure ratios in terms of temperature ratios. Now, what is T0 here? Stagnation temperature. Now what I want? I want stagnation pressure. I want what? Stagnation pressure. So what should be P2 now? P2 should be equal to what? P0. Then instead of T2 by T, I got T0 by T. So here also instead of P2 by P1, I can get what? P0 by P. Okay, so I want to make the second state as stagnation. This is possible when I am going to adiabatically decelerated to zero velocity. Okay, when the final state is brought to rest, one is coming from here, but second state I am going to make it stop. That is called as what? Stagnation. That is called as what? You stagnate it. Don't make it to move. You make it to rest. To zero velocity at the zero elevation. So now what happens? P2 becomes P0. P1 can be simply what? P. Which means this implies what? T2 equal to what? T0. And T1 equal to what? T. So just replace T2 with T0 and P2 with what? P0 by adiabatically decelerating the flow to zero velocity and zero elevation with the definition of stagnation states. The definition of stagnation states. So I can end up with like this: P0 by P1 is equal to T0 by T1 whole power gamma by gamma minus 1. So we can see in the last class we arrived at the expression for stagnation temperature. Now we got the expression for what? Stagnation pressure. One more step. What is one more step? P0 by P1. What is T0 by T1? You substitute from here. What is this one? 1 plus gamma minus 1 by 2 into m square into what? Gamma by gamma minus 1. So now I arrived at an expression for the stagnation pressure in terms of stagnation temperature. So P0 by P equal to T0 by T, which is nothing but what? 1 plus gamma minus 1 by 2 into m square whole power gamma by gamma minus 1. So we got the stagnation pressure. We got the expression for the stagnation pressure. So this relationship is very important. In future classes, I will always refer to, I will be using the isentropic relation. At the time, you should be able to recall this equation. What is that equation? P2 by P1 equal to T2 by T1 whole power gamma by gamma minus 1. Similarly, we can get stagnation density. We can get what? Stagnation density. Okay.